Hello everybody. Let's revise isomerism today. So isomerism is extremely important, right? We deal with various types of questions which involve the concepts of isomerism. When we talk about hydrocarbons, haloalkanes, haloarenes, alcohols, phenols, ethers, we use concepts of isomerism to solve questions based on all these chapters. So isomerism is important, do not ignore it. Under isomerism, we have two major types. One is structural isomerism and the other is stereoisomerism. So let's start with revision of isomerism. We will go through some questions. Okay, so this is the first question. If you look at this question, you will see that they have given us Fischer projections. There are 4 Fischer projections, right? These are the 4 Fischer projections. The correct names of the 4 aldoses respectively are. These are the 4 Fischer projections of the 4 aldoses, and we have options. They have asked us to identify the correct option. So we have to see the names. Okay, so this is the first one. Let's start with this. This Fischer projection is having 2 chiral carbons. These are the 2 chiral carbons, right? Okay, now at the top you have CHO. Everywhere at the top you have CHO. If at the top you have CHO, then you can put number 1 on that. That is, we are doing IUPAC numbering. The same way can be used here, which means the carbon which is of CHO has been numbered 1, right? Okay, now in this Fischer projection, the last chiral carbon is this. This is the last chiral carbon, right? Look at this carefully. If you look at this carefully, you will realize that OH is on your right hand side. H is on the left hand side. When OH is on the right hand side and H is on the left hand side, we will say that it corresponds to capital D configuration. Similarly, look at this. Again, at this chiral carbon, this is the last chiral carbon here in the Fischer projection. Last, how do we say last? That is this first carbon. This is not chiral, but this is the chiral carbon. That means the second carbon is the first chiral carbon, the third carbon is the last chiral carbon. Similarly here also, the second carbon is the first chiral carbon, the third carbon is the last chiral carbon. You have to look at the last chiral carbon in the Fischer projection in order to figure out whether the configuration is D or L. So this is D. Even here, if we see OH lies on the right, so this is D. Here, if you see OH lies on the left, so this is L. And here also, if you see OH lies on the left, so this is L. Okay. That is one thing now. So we have figured out whether it is D or L. So this is D, this is D, this is L, this is L. Now, next is erythros and threos. If you have the OH groups on the same side, then it is erythros. See, OH, OH, same side. OH, OH are on opposite sides in the Fischer projection. So this is threos. OH, OH are on the same side. So this is again erythros. And OH, OH are on opposite sides. So this is threos. Hence, this is the correct option. D erythros. So this is D erythros. This is D threos. This is L erythros. And this is L threos. Next one. Give Sawhorse representation of the following compound. Okay, we have been given a Fischer projection. Since we have been given a Fischer projection, we need to convert this to Sawhorse projection. Let's convert. What is the rule for converting Fischer to Sawhorse? So the rule is very simple. Whenever you have to convert Fischer projection to Sawhorse projection, you have to draw this form. That means you have to draw 2y. That is, if you look at this carbon, from this you have these 2 bonds coming out and this bond goes vertically down. So these represent Y in English. This is Y in English alphabet. Similarly, this is also another Y. So you must draw 2Y. This is one carbon, this is the other carbon. Okay. Next, the uppermost carbon in the Fischer projection is this. And the lowermost carbon in Fischer projection is this. So you have to keep this in mind. In the Fischer projection, the lowermost carbon is this, and in the Fischer projection, this is the topmost carbon, which is this in Sauer's projection. All right. Next, look at this carbon. You have CH3 on the vertical line, so here I will write CH3. On the left, you have H, so left on this side I have put H. OH is on the right, so I will write OH here. OH is on the right. Similarly, look at this carbon. This carbon is having H on its left, so I'll write H here. I'll write OH here. I'll write CH3 here. So this is the correct Sauer's projection, but this is eclipsed. Why is this eclipsed? Because both are in the form of Y. Now in the options, we have staggered conformers. This is inverted Y, this is Y. This is inverted Y, this is Y. This is inverted Y, this is Y, and so on. Which means if you have one Y and one inverted Y, then that Sauer's is representing what? Staggered conformer. Staggered conformer. So let's convert this to staggered conformer. This is eclipsed. If we convert this to staggered, then what will we get? Let's perform rotation around this. Okay. So then we'll have this, right? After rotation around this carbon, if I perform rotation, what will I get? I'll get this. OH appears here. H comes here. Okay. So this is the staggered conformer. Let's check the options. Okay. This one, right? First one. OH here, H here, CH3 upwards, and then H on this left hand side, OH on right hand side, CH3 downwards. Yes. So A is the correct answer. Next. Find out the correct relation. Find out the correct relation. Fine. Now we have only one chiral carbon in this structure. Also, we have only one chiral carbon in this structure. We have only one chiral carbon in this structure. Let's go back to the basic rules. If there is a chiral carbon in front of us, and if we see that there are 4 groups attached to it, obviously there are 4 groups attached to a chiral carbon, and all 4 groups are different. That is why we are calling that carbon a chiral carbon. Now my point here is, if we see wedge, dash as well as normal lines, wedge, this is wedge, this is dash, these are normal lines, right? So if we perform 2 swaps around that chiral carbon, 2 interchanges, then nothing changes, which means nothing happens to the configuration of that chiral carbon. Whereas if we perform only one swap, that is one interchange, then we get enantiomer. Now if I look at second and third, okay, if I look at second and third, and if I perform a swap between H and C2H5, what will I get? Look at the groups. What have I done here? I am performing an interchange or a swap, SWAP, swap. So if I am performing an interchange or a swap between H and C2H5, then C2H5 comes here, H comes here, and I get this. I told you if I perform only one swap around a particular chiral carbon, I get its enantiomer, which means 2 and 3 are enantiomers, and hence I'll say D is the correct option. Only one swap has been done, which means I'm performing a swap between 2 groups. Again, if I perform another swap around that chiral carbon, I'll get the identical compound, which means nothing has happened to the configuration of that chiral carbon. Okay. Now see, the same concept can be used in Fischer projection as well. The same concept can be used in Fischer projection as well. Okay, what is the relation between 1 and 2? If I ask you, then what will you say? Again, look at 1 and 2. Now see, focus on 1. If I perform a swap between H and OH, if I perform a swap. That means OH appears here and H appears here. That means I'll get enantiomer of 1. So 2 is an enantiomer of 1. Look at 2. H has come here, OH has gone there. So 1 and 2 are enantiomers of each other. But there is no such option. 2 and 3 are enantiomers. Already we have discussed it. So the correct answer is D. Which of the following statements is incorrect? Okay. It is possible to separate eclipsed and staggered forms of ethane at room temperature. Now see, conformational isomers cannot be separated or isolated at room temperature because they keep interconverting rapidly. We cannot isolate them, and hence this statement is wrong because it is mentioned here that it is possible to separate, whereas it is impossible to separate. Hence the first statement is incorrect. We don't have to look at the other statements because only incorrect statement has been asked for, and in NEET we know that there is only one correct option. We have already ticked A, so we need not check B, C and D. Okay, again conformational isomerism. So conformers of ethane are being discussed. Which of the following statements is true with respect to the conformers of ethane? Now, whether it is ethane, butane or anything, remember one thing, that conformers cannot be isolated or separated at room temperature. Okay, just now we discussed it. Another important parameter or a point of discussion is this: the bond lengths never change, the bond angles never change, which means the angle between two bonds will always remain the same irrespective of the type of conformer being discussed. Similarly, the length of each bond is, a specific bond which has been talked about. So if I'm talking about a bond between atom A and atom B, then the bond length between atom A and atom B will remain same in all the conformers of that species. So bond angle and bond lengths remain same. This is correct. So both bond angles and bond lengths remain same. Bond angles and bond lengths always will be the same. They will not change if the conformer changes, right? So remember this. Whether it is ethane, whether it is any other species, conformational isomers are different isomers with respect to the orientation in space, but the bond angles and bond lengths will never be different. How many stereoisomers are possible for the following compound? Okay, stereoisomers. Whenever in the exam they ask us how many stereoisomers are possible, we need to focus on geometrical isomers as well as optical isomers. In this species, this is a double bond. This double bond is present. There is no other double bond. Okay. Also, there is no chiral carbon here. There is no special system around which optical isomerism would be possible. There is no allene, there is no cumulene, there is no scope for ortho-substituted biphenyl, nothing of that sort is there. We have just one double bond here. Since we have only one double bond here, we will discuss geometrical isomerism in this case. We will see if geometrical isomerism is possible around this double bond or not. Okay. Around this double bond, geometrical isomerism is possible because this sp2 carbon has two different groups attached to it. The groups are CH3 and hydrogen. Similarly, this sp2 carbon has again two different groups attached to it. One is hydrogen atom and the other one is this entire group. So we will say yes, geometrical isomerism is possible around this double bond, and since there is only one such double bond, we will say there are two geometrical isomers, 2⁻⁴, that is 2. This is the formula, right? If the molecule is unsymmetrical, straight away we'll say that the number of geometrical isomers is equal to 2⁻n, where n is the number of double bonds around which geometrical isomerism is possible. So this is the answer. So one will be the Z form and the other one will be the E form. Okay, hold on. There is a chiral carbon as well. So there are two geometrical isomers, that's correct, but we have been asked to find out the number of stereoisomers. This carbon is a chiral carbon atom, and now total number of stereoisomers will be 4. Hence answer is option A. This carbon is a chiral carbon. So please be careful. See, if I ask you how many geometrical isomers are there, you will say 2, Z and E. But if I ask you how many stereoisomers are there, then the answer is 4. 2 raised to 2 is 4. Now, how is this 2 coming? 2 means there is one double bond around which Gi is possible, and there is one chiral carbon around which OI is possible. OI is optical isomerism. So, one double bond plus one chiral carbon, hence 2. The molecule is unsymmetrical, so 2 raised to 2, 4, and hence answer is 4. So, number of geometrical isomers is 2, but number of stereoisomers is 4. Right? Next question. Compare the melting points and dipole moments of the above compounds. Okay. This is a cis isomer. Both the hydrogen atoms are lying on the same side. This is a trans isomer. We have hydrogen atoms lying diagonally opposite to each other. So this is a trans isomer. Now, melting point of trans is higher than the melting point of cis because trans is more symmetrical. So that is the first thing. Melting point of B will be higher than melting point of A. Okay. MP is melting point. If you look at the options, you will see MP. So MP is melting point. So melting point of B is higher than the melting point of A. Now, dipole moment. Okay. If we look at B, here dipole moment is 0. Why? Because the vectors will cancel out each other. Dipole moment is a vector quantity. This vector and this vector will cancel out each other. This vector and this vector will cancel out each other. So I will say that dipole moment is equal to 0. Here dipole moment is non-zero. That means the dipole moment of A is higher than the dipole moment of B. Because here cancellation is not happening. So dipole moment of A, so I will say dipole moment of A is higher than dipole moment of B, but melting point of B is higher than melting point of A. So let's see which option is the correct answer. So melting point of B is higher than melting point of A, but dipole moment of B is less than dipole moment of A. So true. B is the correct answer. Dipole moment of B is 0, right? It's symmetrical. And this is a polar molecule. Polar means dipole moment is not 0. Non-polar means dipole moment is 0. So melting point of trans is higher than melting point of cis. So melting point of B is higher than melting point of A, but dipole moment of A is higher, which means dipole moment of B is less than dipole moment of A. So B is the option B is the correct answer. Next question. Which of the following isomers are not a pair of enantiomers? Not a pair of enantiomers. Okay, again we can use the same old logic. See, we have only one chiral carbon in each. Around a particular chiral carbon, if we perform 2 swaps, then nothing changes. They will remain identical to each other, the 2 compounds. But if I perform only 1 swap around a chiral carbon, then the 2 compounds are enantiomers of each other. So let's see. This is the chiral carbon in 1. This is the chiral carbon in 2. This is the chiral carbon in 3. And this is the chiral carbon in 4. Okay. Now in the question they have asked us which isomers are not a pair of enantiomers. Not. So if I perform 2 swaps around the chiral carbon, then the 2 compounds will remain the same. That means they are identical to each other. So they are not a pair of enantiomers because they are identical. Let's see which 2 are identical. Perform 2 swaps. Okay, so let's randomly pick this one. If I perform 2 swaps around this, let's say I perform a swap between ET and Cl. So here ET and here Cl. Now these 2 are enantiomers, but again if I perform another swap between ET and H, So let's say here I have H, and now here I will have ET. Now I will say these two are identical to each other. These two are identical to each other. Isn't this same as third? This is third. So 2 and 3 are identical. That means they are not enantiomers. This and this are identical. Why? Again, I am repeating. The first swap was performed between Cl and Et, and then the second swap was performed between H and Et. On doing that, we get third compound, that is this one. And so we say that 2 and 3 are identical. Identical means they are the same. Nothing has happened, no change has occurred. So they are not enantiomers. So 2 and 3 are identical, they are not enantiomers. Next question. Which of the following compounds is optically inactive? Okay. Fine. Which of the following is optically inactive? Now, if there is no chiral carbon, and also if there is no special system like an alene or a system which has capability of showing optical isomerism, or any ortho substituted biphenyl, then we'll say that the molecule is optically inactive. Also, if there is a plane of symmetry or a center of symmetry despite presence of chiral carbons, then also we will say that the molecule is optically inactive. So inactive. So basically inactive means if there is plane of symmetry, the molecule is optically inactive. If there is center of symmetry, the molecule is optically inactive, right? If there is no chiral carbon at all, and also if there is no special system, then also the molecule is optically inactive. So this is active because this is a chiral carbon. If there is only one chiral carbon, then definitely the molecule is optically active. So there is only one chiral carbon here. I repeat, if there is only one chiral carbon in a molecule, then definitely the molecule has to be optically active because there is just one chiral carbon. But if there are two or more than two chiral carbon atoms, then we should check whether plane of symmetry is present or not, center of symmetry is present or not. But now here, for this, I will not check whether plane of symmetry is present or not, center of symmetry is present or not, because there is only one chiral carbon. So if there is only one chiral carbon, straight away we will say that the molecule is optically active. So this is optically active. Okay, this molecule is again optically active because there is only one chiral carbon here. This is a special system. This is an alene, such an alene where we have different groups attached to each terminal carbon atom. So this is again optically active. So this is the only one which is optically inactive. There is no chiral carbon atom at all, right? And also if you see, there is a plane of symmetry passing through the middle of this compound. So D is optically inactive. This is not a chiral carbon, so don't go wrong. This is not a chiral carbon. Sometimes people consider this to be chiral. This is not a chiral carbon. Why is this not a chiral carbon? Because these two groups are same. If you travel from this side and reach towards the opposite side, and similarly if you travel from this side and reach like this towards the opposite side, these two paths are the same, which means there is no difference between this path and this path, which means these two groups are the same. And we know that if a carbon has two same groups attached to it, it cannot be chiral, and hence this carbon is not a chiral carbon atom. Okay, interesting. Which of the following pairs are diastereomers? Okay, look at the fourth option, D option. This is one chiral carbon, this is the other chiral carbon. So we can say there are two chiral carbon atoms in this Fischer projection, right? Now, around this, that is the carbon which is having Me attached to it, around this carbon, no swap has been done. See, compared this and this, OH is on the left hand side, OH still is on the left hand side, H is on the right hand side, H is on the right hand side. So there has been no swap between H and OH. Also Me is here and Me is here along the vertical line. There has been no swap between Me and H. which means around this particular chiral carbon, no swap, no interchange has been done. So nothing has changed around this. But if you look at this chiral carbon to which Cl is attached, now there has been a swap between H and Cl. H has now gone that side. That means in this compound H is on the left hand side, whereas in this compound H is on the right hand side. Cl is on the right hand side in this compound, but Cl is on the left hand side in this compound. So we can say that there has been a swap or an interchange between H and Cl. So inversion has happened around this particular chiral carbon. Inversion. Now what is inversion? Inversion means change in the configuration. So if configuration here is R, then configuration here will be S. If configuration here is S, then configuration here will be R. So there has been an inversion. Why has there been an inversion? Inversion has happened because there has been only one swap. So inversion has happened. No inversion has happened here. So I will say that these two are diastereomers of each other. Now remember, if around every chiral carbon atom there has been an inversion, that means around each and every chiral carbon atom, if one swap takes place, then we will say that the two compounds are enantiomers of each other, provided that there is no plane of symmetry. But here only around one chiral carbon atom interchange has happened. So these two are not enantiomers, these two are diastereomers. So those stereoisomers which are not enantiomers are called diastereomers. These two are diastereomers. Also remember, geometrical isomers are also considered diastereomers. Next question. The correct statement about compounds A, B and C is, okay, look at A. A has two chiral carbon atoms. And now if I look at B, now see, this is interesting. B is nothing but this, right? Let's check. Okay. Look at this. B. Now, in B, COOH is at the top and COOCH3 is at the bottom. If I turn the page on which this is written, now I cannot turn this, but if you write this on a piece of paper and turn the piece of paper, you will see that on turning, you will get this, that is COOCH3 will appear at the top and COOH will appear at the bottom of the Fischer projection along the vertical line. Yes or no? If I turn the page in such a way that COOCH3 appears at the top and COOH appears at the bottom, then what will happen? What will happen then? Look at this, very, very interesting. Try. So, or you can do one more thing. Instead of turning B, you can turn this where A is present. So write A on a piece of paper and then turn A. On turning A again, what will happen? I am not turning the piece of paper in such a way that COOH appears at the top and COOCH3 appears at the bottom. You will get another compound, which means I am making you understand only one thing. If I want to compare whether A and B are identical or enantiomers or diastereomers, I need to see, or I need to ensure that in both A and B, the group along the vertical line is the same at the top. That means if COOCH3 is at the top here, then COOCH3 must be at the top in B as well. And COOH must be at the bottom in both the compounds. After that only I can start comparison. I cannot directly compare now because here COOCH3 is at the top and here COOH is at the top. So I cannot compare this with this. I cannot compare this with this because it will be very difficult for me to compare unless I ensure that the vertical line has COOCH3 at the top in both and COOH at the bottom in both, or the other way around, COOH at the top in both and COOCH3 at the bottom in both. This is the first and foremost thing. Okay, so let's do the other way around. So what we can do is, I'm turning the page in such a way that COOH appears at the top. I'm doing this for A only, so that I don't have to rotate this, I don't have to rotate this, because in both B and C, COOH is at the top. Only in A, COOH is not at the top. I repeat, only in A, COOH is not at the top, whereas in B and C, COOH is at the top. So, I will convert or rewrite A, I will redraw A in a way such that COOH is at the top and COOCH3 is at the bottom. After doing this, I can easily compare whether swaps have taken place or not. So if I convert this to a form where COOH is at the top, then what do I get? So I'll get this. So A is, see, A is COOH at the top, COOCH3 is at the bottom. So I will write here. Right? So this is A. So basically, this is A. Now I can compare easily because in all the compounds, COOH is at the top. So if I compare A and B, clearly what I can see is that around this carbon, swap has taken place. That is, H has gone that side, OH has come this side, which means there has been one swap around this carbon. Similarly, if I look at this one again, there has been one swap around this carbon. That is, H and OH have got swapped, which means around each carbon one swap has happened. That means inversion has happened around every carbon, which means A and B are enantiomers. A and B are enantiomers. So the correct statement is D. A and B are enantiomers. What is the correct relation between A and C? See, A and C are diastereomers because inversion has happened around this carbon only. Around the lower carbon, that is this one, inversion has not happened if you compare this and this. So A and C are diastereomers. Okay. So A and B are enantiomers. What about B and C? B and C. So B and C are again diastereomers. Why? Because inversion has happened around this carbon. If you compare B and C, then look at this, here between H and OH inversion, interchange has happened, one swap has happened, so I'll say inversion has taken place around this carbon, whereas around the topmost carbon nothing has happened. So B and C are diastereomers. So B and C are diastereomers, A and B are enantiomers. So option D is correct. Which of the following does not contain any asymmetric carbon but can show enantiomerism? Asymmetric means chiral. Asymmetric means chiral. Okay, but can show enantiomerism. Okay, so does not contain asymmetric but can show. Let's see. Let's talk about D, 2,3 pentadiene. 2,3 So if I start numbering according to IUPAC rules, this is what I'll get. So there's a double bond between 2 and 3, there's a double bond between 3 and 4. So I'll say the IUPAC name of this compound is 2,3 pentadiene or penta 2,3 diene. Look at this carefully. There is no chiral carbon at all. There is no symmetric carbon here. Still, this is optically active. That means this can show enantiomerism. Anything which is optically active can show enantiomerism. Why? How is this optically active? Because of this. Look at this now. this extreme carbon has two different groups attached to it. Again, this extreme carbon has two different groups attached to it. When we have only two consecutive double bonds, the system is called an allene. So this is an allene. An allene is optically active if there are two different groups attached to the extreme carbon. That is on the left hand side also, if you see that these two are different groups. Also, if you look at this extreme carbon, then there are two different groups, H and CH3 are two different groups attached to this extreme carbon. So you have to look at the extremities of an allene. If each extremity has two different groups, the overall compound is optically active, and so we'll say that D is the correct answer. Because there is no chiral carbon, still although there is no chiral carbon, still this can show optical isomerism, enantiomerism, because remember that there is no plane of symmetry or center of symmetry in an allene. There is no plane of symmetry or center of symmetry in an allene if we have two different groups attached to each extreme carbon. Now see, what about this allene? Is this optically active? This is also an allene, right? There are two consecutive double bonds, so this is also an allene, but this is optically inactive because of these two groups. Look at hydrogen, hydrogen. So both are hydrogen atoms attached to the same carbon. So this is optically inactive. This cannot show optical isomerism. This cannot show enantiomerism. This is optically inactive. So this cannot show enantiomerism. This cannot show enantiomerism because this extreme carbon has identical atoms attached to it. So be careful. Now you will be able to understand why this is optically active. Look at this carbon, there are two different groups. Look at this carbon, there are two different groups. Which of the following represents the structure having cis arrangement around each double bond? Okay, each double bond, cis arrangement around each double bond. So look at this double bond. If I look at this carefully, I can show hydrogen atoms. Now see, both the hydrogen atoms are lying on the same side. So we'll say that around this double bond, the configuration is cis. Similarly, here also. Again, around this double bond, configuration is cis. Likewise, around this double bond as well. Both the hydrogen atoms are on the same side. So around this double bond, the configuration is cis. Cis, cis, cis. Everywhere it is cis. Answer is B, because that is what the question had asked for. Which of the following represents the structure having cis arrangement around each double bond? That means around each and every double bond, the configuration must be cis. So cis, cis, cis. Around this cis, around this also cis, around this also cis. What about C? If I look at C, now see, here we have these two hydrogen atoms attached to this carbon, which means geometrical isomerism is not possible here. Around this double bond, there is no GI. Similarly, around this double bond, there is no GI. Why? Because again, you will have the same issue. Only around this double bond, you will have GI, and the configuration is trans, because these two hydrogen atoms are lying opposite to each other. Again, around this double bond, the configuration is trans, because the hydrogen atoms are lying diagonally opposite to each other. Here around this double bond, it is cis, because these two hydrogen atoms are lying on the same side. Again, around this double bond, there is no GI. There is no GI because of the same problem. Here you have CH2, here also you have CH2. So around this double bond, there is no GI. Similarly, around this double bond, there is no GI. GI cross means there is no GI. If this carbon has same groups attached to it, then around the double bond, GI is not possible. So answer is B. All right, next question. IUPAC name. IUPAC name must incorporate the configuration as well. If there's a double bond around which GI is possible. So if you look at the options, you will see Z, E. Look at this double bond now. Let's try to find out whether the configuration is Z or E around the double bond. Now, how do we decide whether the configuration around the double bond is Z or E? So first we need to apply CIP rules. CIP rules are used to decide priorities of the groups. So let's start assigning priorities. Look at this carbon. Hydrogen is attached to this carbon and a carbon atom is attached to this carbon. Out of hydrogen and carbon, which has a higher priority? So CIP will be used. We know that if the atomic number is higher, then the priority is also higher. Out of H and C, C will have a higher priority because the atomic number of C is 6, the atomic number of H is 1. So this is having a higher priority. Now, look at this carbon. You have Me. Me is nothing but CH3. So it is carbon attached to hydrogen, whereas this is carbon attached to oxygen. Now carbon versus carbon. You cannot compare carbon and carbon because both are same. So you have to look at the next atom to which carbon is attached. Here carbon is attached to hydrogen. Here carbon is attached to oxygen. We know that the atomic number of oxygen is higher than the atomic number of hydrogen, which means this has a higher priority than CH3. I mean, this entire group has a higher priority than CH3. Similarly, here also this entire group has a higher priority than H. So the higher priorities are lying on the same side. So the configuration around the double bond is Z. It is Z. Now, what about the position of this ketone? So let's see now. Position of ketone. So C2H5 is nothing but CH2. CH2 is a 1, 2, 3, 4, 5, 6, 7, 8. Right? So 4, 6 dimethyl oct 4 in 3 on. Right? And the configuration is Z. So Z 4, 6 dimethyl oct 4 in 3 on. One, two, three. So at the third position you have a ketone, right? So 3 on. Ketone is the priority here. I mean, when you talk about the priority series of nomenclature, you see which group is going to be the principal functional group. So here ketone is the principal functional group because there's no other group here, and hence the suffix is on because the suffix is always based on the priority. Ketone is the priority, so the suffix is on, and at the fourth position I have a CH3 attached. At the sixth position also I have a CH3 attached. Hence 4, 6 dimethyl. There's a double bond between 4 and 5, and hence oct 4. This 4 indicates the position of the double bond because you see E and in written after 4. 4 in means double bond is between 4 and 5. 3 on means the ketone is at the third position. And Z, already we have discussed that it is Z. So C is the correct answer. 4, 6 dimethyl oct 4 in 3 on. Now see, do not make this mistake. Do not start numbering from here, because if you start numbering from this carbon, then the position of ketone will be higher. So let's do it and prove. 1, 2, 3, 4, 5, 6. Then the ketone will appear at the 6th position. That's wrong. Okay, the IUPAC name of this compound is. Alright. Now, if you look at this compound, this is how I will number, right? So 1 bromo and 1 phenyl. 1 bromo, 1 phenyl ethane. Alright. Now RS configuration. Here there is no concept of Z or E because there is no geometrical isomerism. There is no double bond between carbon atoms around which geometrical isomerism can take place. This carbon is a chiral carbon. Since there is a chiral carbon, we can assign configuration that is either R or S based on CIP again. So let's do that. Bromine, hydrogen, carbon, carbon. These are the 4 atoms attached. The top priority will be given to bromine because the atomic number of bromine is the highest. The least priority will go to H, right? Then carbon and carbon. But here we say, we can clearly see that carbon is further attached to carbon. But here carbon is attached to hydrogen. So this will have a higher priority. This is how I will get, right? So this is the priority. This is the order of priorities. Now, cover the fourth one and travel from 1 to 3 via 2. So 1, 2, 3. This is how we do, right? We cover the fourth one, we travel from 1, 2, 3 via 2. And then we check whether the movement is clockwise or anti-clockwise. This is a clockwise movement. This movement is clockwise if I go from 1, 2, 3 via 2. And after that, we see where the fourth priority is. If the fourth priority is on a dash, then clockwise movement indicates R configuration and anti-clockwise movement indicates S configuration. So here the movement is clockwise and here the fourth priority is on a dash. So I will say R is the configuration of this carbon. R is the configuration of this carbon. So R, 1 bromo 1 phenylethane. If the fourth priority is on a wedge, then clockwise movement indicates S configuration and anti-clockwise movement indicates R configuration. But here the fourth priority is on a dash, hence clockwise is R. Which of the following is the most stable conformation of 2,3-butane diol? All right, very interesting question. Now, in such a question, we have to see whether the conformer is staggered or eclipsed. Always remember that eclipsed conformers are less stable than staggered conformers. That is the first thing. Okay. Now, here all the 4 conformers given are staggered because one is this and the other one is this. So this is staggered, right? There is no eclipsed conformer. What is eclipsed? This is eclipsed. This is eclipsed. This is eclipsed. These are eclipsed. But if you look at the options, there is no eclipsed conformer at all. So eclipsed conformers are always less stable than staggered conformers. That is the first thing. But then in the options, there is no eclipsed conformer. Okay. Now out of staggered conformers also, we have to remember that if there is scope for intramolecular H bonding, then give priority to it for stability. Okay, so if you look at D, there is intramolecular H bonding between H of this and O of this. If you look at A, there is intramolecular H bonding between H of this and O of this. So between O and H, there is intramolecular H bond in A. Also in C, there is scope for intramolecular H bond. And also in D, there is scope for intramolecular H bond. But in B, there is no scope for intramolecular H bond. So B is straight away ruled out. So B is out. Because in B, there is no scope for intramolecular H bonding. Okay. Now, let's look at A, C and D. In A, C as well as D, there is scope for intramolecular H bonding. Now, the next point to be considered is steric hindrance. So, if large groups are away from each other, if the distance between 2 large groups is too much, then the stability is much higher. And based on that logic, we can see that in C, the 2 CH3 groups are very far away from each other because they are diametrically opposite to each other. In D, they are close. And also in A, they are close. See, in D, these 2 CH3 groups are close. CH3 is a group, right? It's bulky. It's not very bulky also, but it's bulky. Definitely much more bulky than hydrogen atom. So, 2 groups should be away from each other if we want the stability to be higher. And hence, based on that, C is the most stable conformer. Because in C, these 2 groups are far away from each other. Whereas in A, CH3 are, the 2 CH3 groups are not so far away, they are close. Here also they are close. Only in C, these 2 CH3 groups are diametrically opposite to each other. And also in addition to that, we see that there is intramolecular H bonding between OH and OH. So C is the correct answer. Which of the following shows optical isomerism? That means which of the following is capable of showing optical activity or enantiomerism. So this is, yes, it can show because this is a special case. This is called ortho substituted biphenyl. Ortho substituted biphenyl. Now remember, if you have ortho substituted biphenyl, then it may or may not be optically active. I'm not saying that it is always going to be optically active. So you have to check. Now what do you have to check? So check this way. If A is not equal to B, and at the same time you have to check. So if A is not equal to B and also X is not equal to Y, then it is optically active. Then it can show optical isomerism. So A is optically active, COH and NO2, two different groups. So A is not equal to B. Similarly, X is not equal to Y, NO2 and COH, these two are two different groups. B, it's an alene, we have already discussed, these two are different groups, these two are different groups, and hence B is also optically active. A and B are optically active. Now C, just by looking at C we cannot figure out. So what we can do is, we can convert this to Fischer projection. Convert this to Fischer and check whether there is any POS or not. If there is no POS in Fischer, then we'll say that it is optically active. So convert this to Fischer. For converting this to Fischer, we have to remember that this large circle in Newman projection, this is a Newman projection, right? So the large circle in Newman projection represents this topmost carbon in Fischer. Right? And this small dot represents the lowermost carbon in Fischer. If you look at this, this is the only chiral carbon here, and we have discussed already that if there is only one chiral carbon in the molecule is definitely optically active. So answer is D, all are optically active. Okay, how many isomers of C5H11OH will be primary alcohols? Exclude stereoisomers. That means we don't have to count geometrical isomers, we don't have to count optical isomers. Okay, fine. Now, what is the degree of unsaturation of this? This is degree of unsaturation. We need to find out du first so that we know that whether there is any pi bond or not, whether there is any ring or not. We need to find out du so that we are aware of the number of rings and the number of pi bonds. If du is 1, there could be 1 pi bond or there could be 1 ring. If du is 0, there is no pi bond, there is no ring. So we need to check the value of du first in order to get an idea about the number of pi bonds and number of rings. Okay, so if I find out the value of du from here, okay, so what is du? The formula of du is number of carbon atoms minus number of hydrogen atoms upon 2 minus number of halogen atoms upon 2 plus number of nitrogen atoms upon 2 plus 1. So C minus H by 2 minus X by 2, X represents number of halogen atoms, plus N by 2 plus 1, N means number of nitrogen atoms. Here there is no nitrogen, there is no halogen, right? So what is the value of du here? 5 minus 6 plus 1, 5 plus 1, 6 minus, so 0. Since du is 0, there is no ring, there is no pi bond. Let's start drawing the primary alcohols. Now, for solving such a question, we have to start drawing the structures. There is no shortcut, there is no formula. We have to start drawing the structures because the molecular formula has been given. So let's start drawing. 1, 2, 3, 4, 5. This is one alcohol possible. Is this primary? Yes, it is primary because this carbon is a 1 degree carbon. How do you define a primary alcohol? A primary alcohol is an alcohol in which the carbon to which OH is attached is a 1 degree carbon. So this carbon is a 1 degree carbon. This carbon is having OH attached to it. So I'll say that yes, since this carbon is 1 degree, the alcohol is 1 degree. Likewise, you can draw some more. Now see, this is also another alcohol which has this molecular formula, but this is a 2 degree alcohol because this carbon is a 2 degree carbon. But in the question they have asked us to identify only 1 degree alcohol. So I'm drawing only 1 degree, so I'll not draw this. Since due is 0, I cannot draw any ring. I cannot draw any pi bond. So no double bond is allowed, no triple bond is allowed, no ring is allowed because due is 0. Right? Check. So we are basically drawing and finding out. Is this a 1 degree alcohol? Look at this carbon because this is the carbon to which OH is connected. So this carbon is again 1 degree because it is connected to only one carbon here. So yes, this is also a 1 degree alcohol. Keep a track of the number of carbon atoms. See, C5. So there should be 5 carbon atoms. How many carbon atoms here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. So we have 5 carbon atoms here. And all of these are 1 degree alcohols. We are not supposed to talk about stereoisomerism here, exclude stereoisomers, right? So for solving such a question, we must draw the structural isomers. Right? We must draw the structural isomers. So how many 1 degree alcohols are possible which have the formula C5H11OH? The thing is, first we have to find out du, and after du, we'll start drawing. So is there any such alcohol which we have missed out? Let's see one if there is any more alcohol having this formula. Let's check. No. Is this a 1 degree alcohol? This is a 2 degree alcohol. So this cannot be our answer. What about this one? Check this one. Yes. So 2-methyl butanol. This is 3-methyl butanol. This is just normal pentan 1-ol. And this is 2,2-dimethyl propan 1-ol. So there are 4 such 1-degree alcohols. We are not counting stereoisomers because in the question they have asked us to exclude stereoisomers. Okay, next question. The minimum number of carbon atoms in a ketone to show metamerism is. Okay, so look at this now. This is a ketone, right? This is also a ketone. There are 5 carbon atoms. These two are metamers with respect to each other, yes or no? Because here the position of C double bond O is at the third one, here the position of C double bond O is second. So we will say that these two are metamers with respect to each other. So at least 5 carbon atoms are needed in a ketone to show metamerism, which is an incorrect statement. Okay, which is an incorrect statement. Look at this. Now, if you look at the first statement, the first option, this is 1 carbon and this circle is another carbon. Similarly, here this is 1 carbon, this circle is another carbon. If you look at this dot, this small carbon, there are 2 Me, that means there are 2 CH3 groups connected to this carbon. And here, if you look at this carbon, there is only 1 CH3 connected to this carbon, and this CH3 is connected to the other carbon, which means the structure has changed, and hence they are structural isomers. They cannot be conformational isomers. The total number of configurational isomers means what? The number of stereoisomers of the given compound is. So this is 1 double bond around which Gi is possible. This is 1 chiral carbon. And this is another chiral carbon. This is unsymmetrical molecule, so 2 raised to 3, and hence answer will be 8. 1 double bond around which Gi is possible. There are 2 chiral carbons, so 2 raised to n is the formula for finding out number of stereoisomers if the molecule is unsymmetrical. This is unsymmetrical molecule, clearly we can see. So 2 raised to n, 8. Which is a pair of geometrical isomers. All right. Which is a pair of geometrical isomers. Okay, let's look at the first one. So in the first one, Cl and H are opposite to each other in the first compound. Here also Cl and H are opposite to each other. Cl and H are opposite to each other. So these are not geometrical isomers. Here pH and OH are on the same side. Here also pH and OH are on the same side. So they are not geometrical isomers. Let's look at D here. Me are on opposite sides. Here Me are on same side. Yes. So this and this are geometrical isomers with respect to each other. This is trans because 2 identical groups are lying opposite to each other. This is cis because 2 same groups are lying on the same side. So D is the correct answer. Okay, let's look at this now. See, what is happening here? Again, same logic. Let's look at the carbon atoms. Now, in this molecule, H and OH are connected to this topmost carbon, whereas in this molecule, CH3 and OH are connected to the topmost carbon, which means this carbon is the one which has been shown in this way. That means, because if you look at this, CH3 and OH are connected to this carbon. So I will again invert this. I will turn the page and I will redraw this in such a manner so that I can compare easily. So let's redraw this. Look at this now. So this COH has now come here. That is, now it's lying at the top. Okay. This COH is now lying at the top. This COH. Okay. Okay. So these are homomers because these are identical. Now we can compare. Around this carbon there has been no swap. H is on left, H is on left, OH is on right, OH is on right. Similarly here, OH is on left, here also OH is on left, CH3 is on right, CH3 is on right. So this and this are same, homomers. Homomers means same, identical. Right? Which of the following is not a metamer of C4H10? O, not a metamer. See, in metamers, the functional group has to remain the same. In D, the functional group has changed, alcohol. A, B, and C are ethers. In D, we have alcohol, which means D is not a metamer because we know in alcohols metamerism is not possible. So D is the answer. Find the number of stereoisomers of 1,2-dihydroxycyclopentane. Okay, so let's draw 1,2-dihydroxycyclopentane. Now let's start drawing the stereoisomers. If I am putting both OH groups on wedge, this is one stereoisomer. Right? If this OH is on dash and this OH is on wedge, this is the other stereoisomer. And here, if I am putting this OH on wedge and this OH on dash, these are the three stereoisomers. So, now see, A, B, C. These are the three stereoisomers. B and C are enantiomers of each other. A and B are diastereomers of each other. A and C are diastereomers of each other. If you have this confusion in your mind, I would like to clear it. You might feel, why haven't I drawn this one? Why haven't I drawn this one? Now A and this are same because in A there is a plane of symmetry, and because of plane of symmetry it cannot show enantiomerism, because we know that if some molecule has a plane of symmetry it is optically inactive, and if the molecule is optically inactive its enantiomer is not defined, because the mirror image of an optically inactive molecule is nothing but identical to itself. So A and this are same, and hence will not draw this if we have drawn this. Hence answer is 3. Alright. So I hope you have understood all the questions. Keep practicing stereoisomerism more. All the best. See you soon. Thank you.